K-factor of a rigid frame. This is a rigid frame. When you design the column, we have to calculate the K-factor. I will explain the concept of K-factor and then the derivation of the K-factor. This is a portal frame subjected to vertical load P and the horizontal load H. In order to calculate the column strength, we have to calculate K-factor first. K-factor means effective length factor. K-factor depends on the stiffness of column and beam. So different stiffness ratio of column and beam result in different K-factor. The stiffness ratio is called G, is equal to sigma EI over L, column stiffness over L, divided by sigma EI over L, beam. So we firstly calculate this stiffness ratio, column or beam. Beam is connected here. It is a fixed end, then means there is no angle change at joint A. So that means we have the infinite bending stiffness of the beam. So in GA is infinite bending stiffness of this beam. The column equal EI, this one EI over L. So denominator is infinite, so GA result in 0, right? How about GB? GB, this one, column EI over L over beam EI over L. If we assume EI of column is equal to EI over beam, and again column length is equal to beam length, then GB must be 1. If you have this stiffness ratio of this column at the bottom and top, we have alignment chart. It is, as you see, embrace frame. There must be side sway. We have to see alignment chart of embrace case. That is page 287 of your textbook. So GA equal 1, GB equal 1. Let's look at embrace case alignment chart. Result first. This is a braced one. Embraced one is, let's go down. Yes, this one. There is some side sway. So this is embraced case. So GA equals 0. That is the stiffness ratio. Okay. GA was 0, right? You remember? And then how about GB? GB equal 1. So in that case, we connect these 2 points. This point and this 1, 0 and 1. Connect like that. Then we can read this cross point, this value. That is K value, effective length factor. So it is 1.17 something. Okay, so if we calculate GA and GB, then from this chart, you can get K factor by connecting these two values. That is the method. Then go up, K equal 1.15. If you use the scale, then you can get more accurate value from the alignment chart. If you get this effective length factor, you can do member strength check, column strength check using interaction equation provided by design code. That is procedure. I'd like to show some derivation of alignment chart for braced case. This is beam, this is column. First, second, third story. So we take out this part. Now, so if I draw, then this frame, the frame like that. Then we just take out this part. So as you see, there is no side sway. So it is a braced case. So sub-assemblage model of this whole frame, this alignment chart for braced frame. Now let's consider how to derive this alignment chart. When I derive this alignment chart, we have several assumptions. First one is the behavior is elastic. The second one is axial force in beams are negligible. Okay, we ignore axial force of the beam. Third assumption is that all column in a story buckle simultaneously. And then rotations are equal and opposite. This is a brace frame. So this is point A. This is joint B. Then the angle here is theta A, clockwise. the other end, the angle also theta A, but direction must be opposite because it is a brace frame. So this is theta A, this is theta A, this also theta A. Let's look at here, B, theta B, theta B, theta B, theta B. This also theta B, right? This also theta A, theta A. One interesting assumption is that here, this is theta B, this is theta B, this is theta B. These are theta A, here theta A. That is assumption to drive alignment chart for braced frame. Otherwise, if this is not theta A, let's say theta C, this is theta D, then it is very difficult to drive alignment chart. So we have to make the alignment chart that can be easily used by designers. This is assumption. This theta A, theta B, theta B. How to drive? We establish slope diffraction equation. For column, here, MAC1, here, MA, joint is MA. This is column C1, C2, C3. So from joint A regarding this C1, we have to establish slope deflection equation EI over L regarding column C1. And then we have axial force here. So column has axial force. Then slope deflection must be SII theta A plus SIJ theta B. How about MAC2? MAC2. Yeah, we can easily write in the same way. EI over L C2 SII theta A plus Sij theta B. You also can write MBC2 regarding joint B, and then short deflection of equation of this C2. You can write in the same way. How about for beam? See here, this one. So there is no axial force. So slope deflection equation is not SII anymore. Then what is that? For theta A, because there is no axial force. So EI over L regarding B1 for theta A minus 2 theta A. Why minus? Slope deflection equation is clockwise angle is plus. This one is counterclockwise angle. So minus 4 theta A minus 2 theta A. Right? So it results in EI over L B1 2 theta A. Can you write MA B2? That is B1. B2 is also same. EI over L B2. 4 theta A minus 2 theta A. Like that. So it results in EI over L B2 2 theta A. In the same way, you can write this too. As you see here, the unknown is theta A and theta B in slope deflection equation. And then you need two equation. What kind of equation can you have? That is this joint equilibrium at A, joint equilibrium at B. So ultimately you can get two different equation. If you see here, yeah, like that. Equilibrium at A, so you have four equation. MAC1 regarding column C1, MAC2 column C2 regarding beam 1, regarding beam 2, right? So you have this joint equilibrium equation. So if you input the previous equation MAC1, MAC something like that, and then rearrange, you can get this equation ultimately. Equilibrium at joint B, also you can get this equation. Sigma EI over LB, sigma EI over LC. This 1 over GA. GA is a stiffness ratio. So if you rewrite SII, GA 2 over GA, Sij, this one SII plus 2 over GB. You can rewrite matrix form using these two equations, right? Then theta A, theta B, right hand side 0, 0. Okay? In order to satisfy this equation, this determinant must be 0. So if you calculate this determinant, if you input the equation SII, Sij equation, you know that equation. You rearrange, then you can get this equation. GA, GB over 4 pi over K square, blah, blah, blah. Here, Sij include KL, right? So KL equal square root to K equal P over EI, LL, okay? That can be rewrite pi square root to P over PE. So it can be rewrite pi over K, okay? By the way, if you use this relationship, you can get this equation. If you investigate this equation, you have GA, GB, and K. So this equation is a function of GA, GB, and K. So if you determine the value of GA and GB, then you can calculate K, effective length factor. If you get GA and GB, you can calculate K. You make these several data regarding GA and GB, and then you can draw this alignment chart. From that, the many result of K and GA-GB relationship using this equation. Do you understand? That is alignment chart for braced frame. And let's look at the alignment chart for unbraced frame. It looks like this one. The unbraced frame, we have the side sway. As you see here, unbraced frame case, there is a side sway. So at joint A, the angle is theta A. It has the side sway. We have the angle theta A. Angle direction is clockwise. Here also clockwise. Because this is side sway. If I draw something like that, okay? So the angle like that. So this theta clockwise. This angle is clockwise angle, okay? Brace case is counterclockwise angle. Yeah, that is different. And then another different is that we have the side sway. Here also angle theta A, here theta A, theta B, theta B, theta B, theta B, here theta B, or something like that. Different thing is clockwise. Everything is clockwise, the angle. Let's go up. On brace frame, you see the double curvature bending. Yeah, this called double curvature bending. Side sway involved. So finally, you can get the equation 4852. The textbook page 290. Then using those equations, you can draw this alignment chart. In this case, unknown is theta A, theta B, and delta. So you need three equations. Moment equilibrium at this joint, right? The summation of the moment equal to 0. Summation moment at B equal to 0, right? You have two equations, and then another equation is story shear equal to 0. Because there is no lateral load here. From there on, you have three equations. Then you can solve. The resulting equation is 4, 8, 52. Your page 290. Okay, I skip the procedure because of time limitation. And look at the modification of K factor. Using the alignment chart, you can get the K factor. But let's look at this one. If the end condition is changed, what happened? If end condition is changed, K factor must be changed. Because this alignment chart, the beam must be continuous here. Okay, column continuous here. That is the assumption of the alignment chart. If the frame, if this right hand side of the beam end, let's say fixed, then the assumption is different. This fixed condition is different from the original assumption. If this end is hinge, again, this condition is different from the original assumption. Then our calculate K value must be modified. Why? Because the assumption is changed. So how to modify it? Let's look at brace frame. If far end of the girder is fixed, that means like that. Brace frame, some derivation like that, right? This is what? Theta A. This is what? Theta A, right? But how about this case? This far end of the beam is fixed. Then the angle shape must be theta A and 0, like that. This is theta A. This is 0. Originally we assume like that, but we can have this special case. then the K factor from this original assumption must be changed, right? K prime. So how to change it? If far end of Gödel is fixed, then what is the equation? Originally, this case, slope deflection equation is MA. This one, let's say B2, beam. This beam also B2. MA B2, right? Then L over EI, right? Plus 4 theta A. This is minus theta A, right? Then it result LEI 2 theta A, right? For this case. How about this case? This angle is 0. That result in this is 0. The remaining one is what? LEI 4 theta A. So original one is 2 theta A. If a far end is fixed of the beam, that is this one. Okay? EI over L 4 theta A. Yeah, so the exact one is this one for fixed end case. That means it becomes 2 times bigger. So how to represent 2 times bigger? We consider LG prime. G means girdle, yeah, beam, this beam, okay, this beam. Yeah, another term is girdle, okay. So LG prime equal, if we input here original one, EI, LG prime equal LG over 2 and 2 theta A. In this specific case, from this original equation, we replace LG prime. In fixed end case, LG over 2. It results in this one, 2, 4 theta A, right? That is the way to modify K factor for different boundary condition of the far end beam or far end girdle, the same thing. Different than we simulate this different value by changing this beam length. How about hinge case? We can use LG over 1.5. For embrace frame, if a far end of the girdle is fixed, the same way you can derive, then LG prime is 1.5 LG. If a far end of girdle is hinged in this embrace frame, LG prime equal 2.0 LG. You can derive just similarly following this case that I already showed the derivation. And another one is that in elastic stiffness reduction, stiffness ratio, that is beam or girdle stiffness ratio, we have to use LG prime. If the far and the girdle boundary is different, then we have to use LG prime. But in this case, we have to introduce tower IC. Tower means if the column partially yielding, stiffness degrade, Pu over Py greater than 1 over 3. In that case, column stiffness degrade because column section is partially yielded. So we consider that effect. That equation, this one. Okay. If we have the bigger Pu, then we have the small tower. If Pu over Pi is less than 1.3, then there is no inelastic stiffness reduction of the column. Then we can use tau equal 1.0. Another term is that the leaning effect. As you see here, this column is top and bottom is hinge. This center column, top is rigidly connected. This one is rigidly connected. So this column subjected to P1, P2, P3. But as you see, this column, top and bottom is hinged. So this column has no resistance about the lateral sway. This column is leaning the stiffness of the center and right hand side column. Yeah. That is a leaning effect. So these two columns share some burden of this column. That kind of a leaning effect can be calculated. Ki prime equal sigma pu. Sigma pu is summation of the vertical load. If we calculate the K of the center column, then PUI is P2. And II is the stiffness of this column. Sigma ii ki square is that we have least connected column, this one and this one. So we have 2 I. So I2 divided by K2 square plus I3 over K3 square. That kind of calculation in order to consider this linear effect. So that means this column 2 and column 3 helps column 1. That is linear effect. So calculate the linear effect must be greater than square root of 5 over 8 ki. That is linear effect. Let's see you in next lecture. Bye.